All good? Okay. Okay, let's get started. Is this good? Can people hear me? Okay. Okay, today we're going to finish, hopefully, pipeline processor design. Not all the aspects of it, because we're going to continue issues with pipelining next week, but hopefully the basics of pipeline processor design, data dependence handling, and control dependence handling will be clear by the end of today. Oh, okay. So this is, I think, your last reminder for this review, which is due April 1st, which is before our next lecture. Okay, this is what we're covering. We have covered multi-cycle microarchitecture, and we started building a pipeline after that. And now we're going to cover some issues in pipelining. And these are some of your readings. And I'd recommend doing these readings, actually. They're relatively short, and they explain the concepts nicely, especially the H&H readings, which we have covered in lecture last time, if you remember. Okay, just to jog your memory, this was our multi-cycle MIPS processor. And this was our finite state machine. We built this, most of it at least. And we said that we can easily handle multi-cycle memory access. This will come up again in pipelining. So don't forget these issues. These are fundamental issues. And we asked the question, can we do better? And we basically said, oh, we can actually have different instructions in different stages. In this case, 4 instructions in 4 different stages. But you could have, we actually built a 5-stage pipeline, as I'm going to show you soon. Of course, we said we need to be more careful than this. We need to add pipeline registers, etc. Right? So essentially, pipelining is doing multiple instructions concurrently at different stages of execution in a single machine. And we contrasted this with multi-cycle, and you see that we improve throughput significantly compared to multi-cycle processors. Later, if you have time today, we're going to do some more performance analysis a little bit more carefully than what we've done over here. And we'll see that pipelining actually improves throughput, but maybe not as 4x over here. Here, with four-stage pipelining over here, fetch, decode, execute, write back, these are the stages, you get 4x improvement in throughput, but life is not that beautiful, as we will see today. We're going to cover those issues today especially. But before that, let me cover a little bit more about how we actually designed the pipeline. We actually started with a single-cycle microarchitecture. So that's the beauty of single-cycle microarchitecture I said yesterday. It was there. We discussed it for educational purposes. We designed a single-cycle microarchitecture a few lectures ago, and this is something hopefully you remember. There are no internal microarchitectural registers over here, as you can see, right? Everything happens in a single cycle for every instruction. And you know this, we designed the data path for it, and then we designed the control logic for it, and we went through the exercise of actually which control signals should be asserted for which instruction, right? Okay, so this was designed, there's no magic, right? So how do you do a pipeline design? Basically, if you want to design a pipeline processor, you go through the same process that we have gone through for both single cycle and multi-cycle. You need to design the data path first, and then you need to design the control logic later, okay? That's what we've done for every processor that we have designed so far. So a pipeline data path design. What is a pipeline data path? Essentially, you start with a single cycle data path. We've already designed the single cycle data path. Let's start with that. And then you decide how to break it down into stages. And we decided to break it down into 5 stages, if you remember yesterday. Fetch, decode, execute, memory access, write back. We're going to keep that 5-stage pipeline. It doesn't need to be 5 stages. Someone could decide to break it down into 4 stages, 8 stages, 20 stages. Some existing processors are actually close to 30 stages. So the goal is to really break it down into different stages so that you improve the clock frequency, right? That's the goal. So once you decided how to break it down into stages, and there's actually a lot of science in this area that we're not going to go through exactly how you do it. That's not the subject of this course. Assume that we've broken it down into stages. We add pipeline registers so that you can separate the stages from one another. You need to add pipeline registers so that the thing that's done in one stage, in one cycle, doesn't affect what happens in another stage at the same cycle, right? So each stage has a pipeline register that's the output of it, which is the input of the next stage. And during the clock cycle, you do some processing in that stage, and the contents of the register doesn't change. Only at the end of the clock cycle, at the rising clock edge, if you remember, we update the contents of the pipeline register such that the instruction in the previous stage finishes the previous stage and moves to the next stage. Does that make sense? Our goal is to basically keep processing instructions, keep moving instructions from stage to stage. And every cycle you do something in each stage. At the end of the clock cycle, you finish what you're done, latch it at the end of at the pipeline register at the end of the stage, and the next cycle will start with what you have latched in the previous cycle to the register. Okay, so these are that's the purpose of the pipeline registers. I'm going to show you again pictorially this thing. Okay, once you add the pipeline registers, you need to propagate the data signals, right? And data signals, we already have a data path. Data signals are clearly propagating because we designed the single cycle data path. But now you need to decide where those data signals need to go. Not all data signals are needed by every stage. And whenever you have data signals available, they are not necessarily needed in the next stage. They may be needed in the next stage, right? So you need to propagate those data signals to the appropriate stage, which means that you need to store those data signals in the pipeline registers, okay? And we've seen that also. I'm going to show it to you again. And also, on top of this, you need to make sure correct action is done in the correct stage. What do I mean by this? You need to ensure that the data signals go to the right place. You cannot basically send the data signal to the wrong place. And we're going to look at that. Basically, this is actually true for control signals also, because control signals are part of the design of the data path, not the control logic necessarily. But essentially, whenever a wire crosses stage boundaries. For example, when we're writing the ALU result to the register file, there's a control signal that says you need to write to the register file. That control signal should be generated in the right stage, right? Meaning the instruction that's in the write back stage should be able to write to the register file and not the instruction somewhere else. Okay, this will be also more clear when we actually go through the design. Okay, once we design the data path correctly, hopefully, you need to design the pipeline control logic. And we already said control signals are essentially the same as a single cycle. So that's the beauty of single cycle. You have the control signals, you have the control logic. That works for pipelining also. Not quite, because pipelining does multiple instructions concurrently, which means that when you generate the control signals, you need to propagate them to the stages where the control signals are needed. Right? For every control signal, you need to make a decision. This is the stage when I actually need that control signal. And to be able to propagate that, let's assume that you generate the control signal in the decode stage. This is one of the options that we discussed yesterday. I'm not going to go through the options again. You don't need it in the next stage, which is the execute stage, but you need it in the memory stage or write back stage. You need to propagate those control signals in the pipeline registers. Okay? Then the goal is to make sure that the control signal travels with the instruction such that you take action, you take the right action at the right time based on the partitioning that you've done for the pipeline. Okay, so you need to extend the pipeline registers to do so, and I've given you a picture of that. I'm going to show you again. Okay, is this all clear? Yes.
Why don't we use multi-cycle and pipeline at the same time?
Okay, what would be the benefit of that?
We could increase the clock frequency and still have the pipeline as a benefit.
Okay, but how would you like combine both of them? So multi-cycle's goal is to really, in a sense, in the multi-cycle, in pipelining, you're really multi-cycle, right? Each instruction is really multi-cycle. Pipelining by itself is a multi-cycle paradigm, right?
True, yeah.
Each instruction is going through 5 stages, for example, in our 5-stage pipeline. So it's by itself multi-cycle. Does that make sense? Okay, good. Okay, good questions though. I mean, you guys should think, and the thinking is good. That makes you ask questions like this. And actually, there's a combination, but I'm not going to go into that combination right now. That's a different kind of combination. Okay, so let's go through what I just said. I went through this yesterday, but I'll go through it a little bit more today. But this is our single cycle processor. It's really the data path mostly, one version of it, but we built it earlier. You remember, we have the instruction memory over here, register file, ALU, data memory, and the writing back action over here. And we basically first need to divide this into stages, right? That's the first thing you need to do. Let's assume that we decided the first stage should be the fetch. The second stage should be a register file read, decode, and control signal generation, which I'm going to show later. The third stage should be ALU, execute essentially. The fourth stage should be memory access. The last stage should be write back. So that's what the stages each instruction goes through. And each instruction does fetch here, decode here. That's why this is called IF, ID. And then execute here, memory access here, and write back here. So we don't write back data from anywhere else but the write back stage into the register file. Make sense? We write to memory in the memory stage. That's a different write. But we write to the register file in the write back stage. Okay? And every instruction goes through these stages. So by definition, it's a multi-cycle thing. But every instruction is going through the same stages. Okay, so we also added, once we divided our single cycle data path into 5 pieces, let's say, we also added these pipeline registers, as you can see. These are registers that are going to store both data signals as well as control signals. Let's take a look at the sum of the data signals. These may not be all of the data signals. But for example, here, after you fetch, you store the instruction bits. We called it the instruction register in the past. You can think of a part of the pipeline register storing the instruction register, right? We also store PC+4 because we're actually going to need it in address calculation, as you can see. So any data signal that you're going to need later on for the execution of the instruction, you should really propagate down the registers. So in the first cycle, you fetch this instruction. In the next cycle, you decode. In the decode stage, this PC+4 gets propagated directly to the next register, because you don't use it here. We're going to use it later on, actually, but you don't use it currently here. But you'll use it in the next stage, which is the execute stage for some things, like branches, right? And also, we read the register file and we store the outputs of the registers, essentially the data values of the two registers that are read. And we also store the sign extend immediate. And these are going to be needed for execution of different instructions over here in the next stage. Okay, so I could keep doing this essentially. Here you calculate the next PC based on PC plus 4 and sign extend immediate left shifted. And then you store it at the end of the execute stage and the execute to mem registers, execute/mem stage registers. ALU output is also stored over here. And look at, there's curiously something called B over here. What is that B? This B is really the register, the second register that you have read. So we directly propagate it from the execute stage input register, IDEX register, to execute to mem register without changing it because it's needed for stores. Whenever you're storing, you need to actually take the data from the register file and write it into memory, right? So you propagate all of the data signals that's needed across the pipeline stages. Yes?
Is it not problematic that this muxer in the end goes back to the registry file?
So is it not problematic, this mux? It's not actually.
That it goes back into the registry file without, there might be something else in the pipeline.
That's true. So we're going to talk about that. If that something else is not reading that register, it's not problematic. So what does this mux do? Let's take a look at it. This mux is, or this wire. Yes, you should always be careful with these wires. The goal of this wire is to really write the data into the register file. And you write the data from this instruction over here, right? So the instruction, once an instruction reaches the write back stage, if it's writing to the register file, it writes the data. If it's a load, you write the data that is latched in the previous cycle while the load was in the previous stage from memory. If it's an ALU operation, then you write the data that is the result of the ALU, right? As we have seen in the single cycle data path, actually. So basically, you should be writing the data, no question about that. This is not problematic as long as nobody else is reading the data, right? Does that make sense? As long as there's no other instruction previously, there's no other instruction in the previous stages of the pipeline, meaning there's no other younger instruction, then you can write that data without problem, right? And we're going to get to this. We're going to cover all of these issues, okay? Okay, so hopefully it's clear. So now we went through almost the entire pipeline, and this is how you construct the data. And you need to ensure that no resource is used by more than one stage. So here, for example, when we're writing the data over here, this write port is not used by anyone else. Only this register. Now, only this instruction, the write back stage. Now, this becomes problematic if someone else is trying to read that register, right? Or if there's another instruction that's over here that should have already read that register. Think about it. We're fast forwarding a little bit, but so far we're kind of assuming an ideal pipeline. Okay, so control points in the pipeline. This is essentially our single cycle pipeline processor that we just designed. It's the same thing with a slightly different view with some control points added. So this was the data path design. Now I added the control points over here. So control points are essentially the same as what we did with single cycle. If you remember the single cycle processor, we had a reg write signal. We had some other signals over here to make sure the instructions execute properly. We have exactly the same signals. Nothing has changed over here. You still need to generate the control signals, and that control logic is essentially also the same. You still have the same control unit over here based on the instruction register. The major difference is you delay the control to the proper pipeline stage, right? So for example, when you're in this stage, you're not writing to a register. The instruction in this stage is actually reading from registers, right? So the control signal, reg write, should not be coming from the instruction in this stage. The control signal reg write should be coming from the instruction in this stage, because that's the only stage where an instruction can write to a register, okay? Which means that when you generate the control signal, when you decode the instruction, you figure out, oh, this instruction writes to a register, so a reg write should be set. you place that control signal into this pipeline register and propagate it and use it when it's really needed. Make sense? So you can see that this signal over here is the reg-write signal. And it's used only, it's connected to this pipeline register over here, which is the write-back pipeline register, which says that the instruction in the write-back stage is supposed to write to the register file, because that control unit, when it decoded the instruction 3 cycles ago, it set that signal appropriately, hopefully, because it's an instruction that tries to a register. So we're going to connect that register, that control signal in that register, into the reg-write signal of the register file. Make sense? Okay. Similarly, we need to propagate the signals that are needed in the memory stage. So we generate, this control unit generates some signals that are needed in the memory stage, especially important for memory instructions, but for other instructions also. Other instructions should do no harm to memory, let's say. And when an instruction reaches the memory stage, it takes the appropriate signals that are needed in the memory stage and uses them. For example, if it says store instruction, mem-write signal should be set, mem-read signal should not be set. And as a result, we write the address coming from this pipeline register, which was calculated in the previous cycle, previous stage, through the ALU. We write to that address the data that's coming from this register, which was latched directly from this register in the previous cycle, which was read from the second port of the register file. Hopefully this all makes sense, right? The instructions are moving in the pipeline, and you need to move the control signals appropriately as well. Yes?
What if we have one blocking part? Like, for example, if reading takes longer than expected.
Okay.
How do we stop
I'll say patience again. Sorry, very good though. Essentially, you guys are thinking ahead. So if there's something, for example, if the memory takes more than one cycle, right? That's what you're saying. Essentially, this pipeline currently doesn't handle that. But we're going to talk about how to handle that. Essentially, okay, let me answer the question. If we are assuming everything is moving. So the assumption right now we make is everything is moving. You keep the pipeline always moving. There's always instructions coming in. They keep going through without any trouble, right? The pipeline is flowing, in other words. If something blocks the pipeline or stalls the pipeline, we're going to call it a stall, you need to stop the pipeline. Meaning this instruction here is accessing data memory. It takes 5 cycles, meaning that this instruction cannot move anymore. What do you need to do? You need to make sure nobody moves. Nobody in the previous parts moves. This instruction over here doesn't move. This instruction over here doesn't move. This instruction over here doesn't move. And what happens here, this instruction cannot move to the next stage, so you actually insert a no operation. You kind of basically insert a bubble, but we will get to that. That's a very good question. And this is going to be our strategy for handling any kind of blocking or stalling, whether it's because a long latency operation or it's because of a dependence, as we will see soon. Okay, so I've already discussed this control signal, so hopefully it's clear. This is actually where we left off yesterday, but I want to discuss things a little bit more so that hopefully everything's a little bit more clear right now. Any questions, thoughts? Okay, now that we've covered some of the basics, let's go through another pipeline over here, a little bit more basics. This is what your book develops. Actually, your book is also very nice in pipelining. It's chapter 7.5, if you're interested in reading it. It does essentially the same thing I did. This is the single cycle processor that your book developed. And it basically breaks it down into 5 stages: fetch, decode, execute, memory, write back, as you can see. And it adds pipeline registers. And it has this instructor part. You can see that there's the write reg signal over here. And we ask the question, is this correct? So basically, assuming an instruction is supposed to write back to a register file over here, because the data value is available only after here, right? For memory instructions, for ALU instructions, it's really available over here. Writing the data value into register file here is wrong, right? Because you'd be writing the wrong data value, which is coming from here. So the control signal over here is coming from this instruction, whereas the data signal is coming from this instruction. Now you should never do that, right? If you're writing some data, assuming it's writing it at the appropriate stage, you should use the control signal at the appropriate stage. So basically, this is how you fix the problem. You propagate the write reg signal over here, and you assert that write signal from the write back stage. Essentially, the control signal must arrive at the same time as the data signal. Okay, and this is all based on the semantics of the instruction, clearly, right? If you're actually using a control signal that belongs to some other instruction, it makes no sense, because we've divided the machine into 5 different instructions. You should use the control signals that you propagated for the right instruction. Okay, I think I've harped on this enough. So this is the pipeline control that your book develops. It's essentially the same as single cycle processor's control unit, and control is delayed to the proper stage. And again, I would recommend that you take a look at your book. Okay, so basically, we've covered how to design the pipeline data path and control logic. Now the question is this sufficient? And as multiple of your colleagues already kind of hinted at, this is not sufficient. Basically, there are 2 major questions, at least 2 major questions. I'm going to expand this. How do you handle dependent instructions? If an instruction that comes later in the pipeline is dependent on a previous instruction, for example, you have a load instruction. Load instruction goes here in the pipeline. An add instruction is dependent on it. Can the add instruction be here while the load instruction is over here? And the answer is no, because load instruction did not generate its result yet. Add needs that result, so add cannot be computing anything if it didn't get that result yet, right? That's the idea. So you cannot keep the pipeline moving. You need to stop the pipeline when you detect a dependence between instructions. And as you have also mentioned, if there's like multi-cycle memory access, it's a similar issue. You need to stop the pipeline. We're going to talk about that. But there are other issues, so I'm going to talk a little bit more about this ideal pipeline. You've seen the slide before. Essentially, an ideal pipeline requires identical operations, same operation repeated, independent operations. There should not be an add dependent on a load, and uniformly partitionable sub-operations. Basically, you can divide everything uniformly to sub-operations. Unfortunately, an instruction pipeline violates all of these. You don't have identical operations. You have different instructions. Not all of them need the same stages. And we are forcing different instructions to go through the same pipeline stages. Now, this is not a bad evil, let's say. We're going to also fix this a little bit when we talk about multi-cycle execution next week. But it causes external fragmentation, meaning some pipe stages are idle for some instructions. And we saw that yesterday, right? An R-type ALU instruction, an add instruction, goes to the memory stage, and it does nothing in the memory stage, right? Okay, so we've seen this. That's called external fragmentation. Okay, there's also uniform sub-operations. Let me cover that first. Different pipeline stages are really not the same latency, and we also talked about this yesterday. But you have to force each stage to be controlled by the same clock. And as a result, you have some internal fragmentation in the clock, which means some pipe stages are fast, but still have to take the same clock cycle time. So you lose some performance from there also. Okay, and now let's get to the independent operations part, which will essentially consume quite a bit of our time in this lecture and the next lecture and the next lecture as well. Essentially, a huge problem is instructions are not independent of each other, right? This is not like the laundry loads. Laundry loads are independent of each other. There's no dependence between my laundry and your laundry and your laundry or something like that, right? Or my different laundries. I can mix and match also, right? So basically, you need to detect and resolve inter-instruction dependencies to ensure the pipeline provides correct results. So our pipeline that we built is not correct yet. It is correct under some conditions where instructions are all independent of each other and memory is one cycle. Quick. There's no stalling condition, basically. So basically, this leads to pipeline stalls, meaning pipeline is not always moving. There will be conditions under which the pipeline stops. Okay, this brings us to a lot of exciting issues in pipeline design that has enabled a lot of creativity and creative solutions. And we're going to see a lot of these creative solutions. So balancing work in pipeline stages, that's not something we're going to see. How many stages and what is done in each stage? This is still an issue. It's always an issue, but it needs to be dealt with. So this is the part that's really interesting and exciting, I think. And this will enable us to build up to out-of-order execution. So we want to keep the pipeline correct, moving, and full. And we want all of them, actually. These are actually, if you think about it, these are different things. But all of them together makes the pipeline good. In the presence of events that disrupt the pipeline flow. So what are those events that disrupt the pipeline flow? Data and control dependencies. We're going to spend a lot of time on these. Resource contention. If two things need the same resource at the same time, what do you do? handling long latency multi-cycle operations, like long latency memory accesses, long latency instructions, and multiply maybe longer latency than an add, for example. How do you handle that, right? And then handling exceptional conditions like where a problem happens in instruction execution. You divide an instruction, you have a divide instruction, and you divide by 0. That's an exceptional condition. What do you do, right? What happens when an interrupt comes in and interrupts a processor? We're going to talk about that next week. So basically, we want to improve pipeline throughput by minimizing stalls. But let's talk about these stalls first. How do we actually handle stalls? So what are the causes of pipeline stalls? So what's a stall? Essentially, I kind of defined it earlier, but more formally, it's a condition when the pipeline stops moving, right? Or it should stop moving if you keep it correct, right? So there are 3 major causes of stalls. One is resource contention. I'm going to quickly talk about it, but we're not going to dwell on it that much. The second one is dependencies. We're going to talk a lot about that. These are dependencies between instructions, data dependencies, where an instruction needs the result of another, and control dependencies, where an instruction is the fact that you need to fetch an instruction is dependent on the fact that you fetched and executed the previous instruction. Okay? And then there's the long latency multi-cycle operations. Okay, dependencies are also called dependencies, or your book calls it less desirably hazard. Hazard is a very alarming term, I think. I think it's just a dependence, basically. You have, essentially, these are there because you need to have ordering requirements between instructions, right? If an instruction needs the value of another instruction, there's clearly a dependence, flow dependence between those 2 instructions. So there are 2 types of dependencies, data dependencies and control dependencies. Resource contention is sometimes called resource dependence. I think this is correct, actually. You're dependent on the same resource. It's not like a hazard. But it's a very different form of dependence. It's not inherent in the semantics of the program, right? It's basically a hardware dependence. So it's really not fundamental to the program semantics, so we will treat it separately. In fact, that's what I will treat first. So let's talk about handling resource contention. This happens a lot when you design a pipeline. It happens when instructions in 2 pipeline stages need the same resource. So whenever you're designing the data path, you need to be careful about it. Also the control logic, of course. So how do you actually handle this? First, eliminate the cause of the contention, right? Basically replicate the resource. We kind of did this with the dryer, right? Earlier. So that we could keep the pipeline moving, we actually had 2 dryers. Duplicate the resource or increase its throughput. Use separate instruction and data memories, for example, caches as we will see, or use multiple ports for memory structures. This is obvious, hopefully. The second solution could be, okay, I don't have enough, let's say, money to replicate my resources, so I'm going to use a single resource, but detect the resource contention and stall one of the contending stages. Right? That's also possible, right? This we're going to, of course, add the stalling logic later on, but it's possible to handle it this way. The question is, which stage do you stall? For example, what if you had a single read and write port for the register file, and an instruction in the write back stage needs to write to the register file, and an instruction in the read stage or register read stage needs to read from the register file? Clearly, you should stall the instruction that needs to read, right? Because you need to keep the pipeline moving. The older instruction is the instruction that needs to write to the register, and it should, once it writes to the register, it'll get out of the pipeline, right? So prioritize that instruction and make sure it writes to the register file first using the single port that you have, and other instruction will read from that same port later on in another cycle, for example. So you need to add control logic to detect these things. Okay, there's one trick that your book assumes, and a lot of books actually assume also, which may or may not be realistic and depend on the design. I'm going to tell you that trick. So with careful design, the register file can be read and written in the same cycle. I will not go through exactly how this is done, but you can, essentially a register file write takes place during the first half of the cycle. You can design the register file to be that way. And register file read takes place during the second half of the cycle. Okay? This way, you kind of handle this resource contention that I kind of talked about, right? At least this particular one. So a read or write from and to the register file has only half a clock cycle to complete. Now, if you do this, there's one benefit. Let's take a look at these instructions. These instructions are not really ideal, but for example, this instruction writes to register 2 in the first half of the 5th cycle. Now, if another instruction needs register 2, they can do it in the second half of the 5th cycle. Okay, this is our pipeline. Load instruction first cycle in the fetch stage, second cycle in the decode stage, third cycle in the address generate ALU stage, fourth cycle in the memory stage, fifth cycle, it writes to the register file. In the first clock cycle, first half of the clock cycle, or the fifth clock cycle, it does this writing. And then you can see that the instructions are pipelined. If an instruction needs that register, it can read it in the second half of the fifth clock cycle. So this instruction can basically read from S2 in the second half without any problem. Okay? Later instructions can, of course, read from the register file, right? Yes?
Is it cached or simply?
It's written, basically. It's simply written. We're assuming that the structure of the register file
simply takes the value is written and at the same time puts it into the other instruction that reads it.
So basically, you have a register file, right? You have 8 registers, let's say. You're writing to register 2. The write to register 2 completes within the first half of the clock cycle. And anything that needs, that reads that instruction in the same clock cycle will get the correct value in the second half. Okay? So the assumption is that you need only half of the clock cycle to write to the register.
Couldn't we simply pass it directly to the
Okay, we're going patience. I like saying that to you. Sorry, but you're thinking ahead. Yes, you could also pass it directly. We're going to see those direct passing, direct forwarding. We're going to call it forwarding. Okay, very good. Okay, but this is a trick. This is actually a forwarding trick. I call it internal register file based forwarding. But this enables you to actually do the write in half of the cycle and read in the second half. Okay. Okay, let's talk about data dependencies now. But before I talk about data dependencies, maybe in this figure, I will illustrate something. This instruction is writing to register 2 in the first half of the fifth cycle. If this instruction were dependent on that, this pipeline cannot be moving like this, right? This instruction needs to wait until it can read the value from the register file or somewhere else, as we may get to later. Okay, so let's talk about these data dependencies. So there are 3 types of data dependencies. One of them is real, the other 2 are fake. The real one is flow dependence. It's also called true data dependence, read after write dependence. This is where an instruction is writing to a register and then later instruction reads from that register. So you truly have a data dependence between the producer of the register and the consumer of the register. And then we have anti-dependence and output dependencies. These are fake, but they still affect the pipeline, depends on how you do the dependence checking, etc. Essentially, we need to be careful about them still. And we're going to actually eliminate them when we talk about out-of-order execution. So which one causes stalls in a pipeline machine? Essentially, for all of them, we need to ensure semantics of the program is correct. I'm going to show you the anti and output dependencies with a pictorial example soon. Flow dependencies always need to be obeyed because they constitute true dependence on a value, right? You communicate values between instructions. Anti and output dependence exist due to limited number of architectural registers. For example, anti-dependence or output dependence means write after write. An instruction is writing to register 5, a later instruction is also writing to register 5. These may have no relationship with each other. They're just names, dependence on a name, which is register 5, right? You don't have enough architectural registers, so compiler allocated register 5 to both instructions. Okay, so that's what I mean by it depends on a name, not a value. This will become a lot more clear when we talk about register renaming and out-of-order execution later on. So we will later see what we can do about them. So let's take a look at these dependence types. So flow dependence. So these are our operations, let's say. It can be any operation over here. Pick your favorite operation. But the first one does something to register 1 and register 2 and stores the result into register 3. The second operation that comes after this reads register 3, which means that it's dependent in a true manner to the previous instruction. And this is a true dependence because this register is really communicating a value produced by the first instruction to the second instruction that needs that value for computation, right? This is absolutely necessary. You could change register 3 to register 1000 here if you have it. You have to change this to register 1000 also, right? Does that make sense? Because one instruction is producing the value, the other instruction is consuming the value. So you need to supply the value from somewhere. And the realization is that we're going to supply this value not necessarily from the register file soon. Okay, so anti-dependence, it looks like this. The first instruction, the older instruction, is reading from register 1. the younger instruction, the next, it happens to be the next instruction, is reading from register 1. Oh, sorry, writing into register 1. Read, write after read. There's a write that happens after read to the same register. Now, if you think about this, these registers have, the values stored inside the registers have nothing to do with each other, right? There is some value in register 1 that's needed for the previous instruction. This instruction overwrites that value. It doesn't need register 1. So if you had more registers, let's say I have my favorite register 1000. If I change the first one to register 1000, I don't need to do anything to this. That way I've eliminated that dependence. That's why this is not a true dependence. That's a false dependence. It's fake. The reason it's there is because we don't have enough registers. And we're going to see this problem over and over. Why don't we have enough registers? Because we cannot have a huge register file. That's one good answer. The other good answer is if you have thousands of registers, our encoding of the registers in the instruction set will be huge. So our instructions will be huge, right? So there are multiple answers to this. Yes?
Even if we don't have enough registers, why is this a problem if we write to the register after we have read?
Okay, so why is this a problem? Basically, the problem is you need to still design the pipeline to make sure you don't get the wrong value. Okay? So this is one of the reasons why we write to register 1 at the end of the pipeline stage. Okay?
Yeah, but then we always write after we read, right?
Well, not necessarily. If you have a pipeline processor, if you didn't design it correctly, you might actually, let's say this is the next instruction. This somehow, anyway, maybe this is not the best example, but it's possible to imagine that there will be some case where you could write to this register and this one incorrectly gets the value. Okay? Yeah. I cannot demonstrate it right now, but yes. Okay. The output dependence is another example of fake dependence. Here you see this instruction is writing to register 3. And there's something that's happening. There's an instruction that's dependent on register 3. And then this instruction is also writing to register 3. And again, the realization is that if you had enough registers, you could rename this one, the bottom one, to R1000, and nothing would have to change, and there would be no write after write dependence. Okay? So basically, you need to be careful with these anti and output dependencies. They still consume some of your resources, and also, if you somehow, you don't want to reorder the writes, right? If you always write to a register at the end of the pipeline, when the instruction is the oldest, then hopefully you will not run into any problems in terms of anti and output. But with flow, there's still a problem. You need to supply data value. Okay. Okay, so this is our pipeline. Basically, let's see two instructions flowing over here, a load word and an independent sub. If it's independent, there's no problem, right? Okay, everything writes back at the end. So basically, the way to solve the anti and output dependencies is to make sure writes happen at the very end of the pipeline and in an in-order manner, right? Okay. So what if a sub were dependent on load word? And that's what we're going to deal with right now. And these are some readings. Actually, these readings I already mentioned. But I'm going to also recommend this reading because it's going to be useful later on when we talk about interrupt and exception handling, out of order execution, superscalar execution, all of those we're going to cover. And it also covers the dependencies and their types and their handling in a nice way. So I'd recommend you take a look at that. Okay, so anti and output dependence are easier to handle, as you kind of guessed. Write to the destination only in the last stage and in program order. Flow dependencies are more interesting and challenging. And there are actually 6 fundamental ways of handling flow dependencies. We're going to cover some of them. A lot of them require detection. You detect the flow dependence, and you wait until the instruction that's producing the value writes the value into the register file. Okay? Detect and wait, basically. You detect the flow dependence and forward the data from the producer instruction to the consumer instruction whenever the producer produces the instruction. You don't wait until the data is written to the register file. These are 2 different things, as we will see. You detect that there is a dependence and eliminate the dependence at the software level. So software figures out that 2 instructions are dependent on each other, and I should separate them a little bit. so that they don't cause problems to each other in the pipeline. This is actually a very powerful technique if you can do it. And then you detect the dependence and move it out of the way. This is going to be out of order execution. We're going to talk about that. There's another approach, which is predicting the value, which we're not going to cover. You say, oh, I have a dependence. I don't know what to do, but I'm going to guess. I think my value is going to be 0, right? Or based on some records I've kept in the past, which is going to be what we will do later in lectures 16, etc. I'm going to guess. And you execute the instruction, but if you're wrong, you need to do something about it. Okay, you need to basically fix the problem. Yes?
Why do you want to move them far apart? Why not move them closer together and kind of forward the data?
Assuming you're forward, yes.
If you can.
Yeah, if you can forward, yes. If you can forward, you can also try to move them closer, but moving them far apart eliminates the dependence, essentially, in the pipeline. You don't need to do anything in the pipeline. Okay, yes? I cannot hear you very well. Go ahead. Yes. Not this one. It's a different prediction. We'll talk about branch prediction later on. Okay. And then there's do something else, which is one of my favorite solutions. We're going to talk about that hopefully later today. This fine-grained multi-threading. And the idea, let me give you the basic idea, because all of these are actually creative and nice ideas that have each led to a lot of different types of research. Do something else means execute from a different thread that you know is independent. So the next instruction comes from some other thread, some other execution context. And you know that they're independent, so you don't need to do anything, right? Of course, there are upsides and downsides to this. Modern GPUs do this, for example, and we will see that in later lectures. Okay, so let's talk about this detection, because a lot of these require detection, right? How do you detect the dependence? But before that, let me show you the problem, basically. So this is a 5-stage pipeline, and I have these adds over here. And the first add is writing to register A, and all of these other adds are kind of implicitly reading from, not implicitly, explicitly reading from register A. But I'm showing this as an example, right? So if you actually, we're assuming that write happens at the end of the write back stage. We don't have this clever trick where you are able to write to the register file in the first half of the clock cycle, right? If you have that clever trick, you can do a little bit better. But basically, if this instruction comes into the pipeline, it's decoding, it needs to read the register A. If it reads register A at this point, clearly there's a problem, right? It's going to read the wrong register A because this instruction writes to register A only at this point, right? Similarly, these instructions will get the wrong value also, if you don't do something about it, of course. Only this instruction will get the right value, right? Make sense? And the later instruction will hopefully get the right value also. So basically, you need to do something about these instructions. You cannot just basically let them flow through the pipeline, right? Okay, so how do you do that? So basically, here, let me finish this. You have a write back. This is instruction I. In the general case, you have instruction I. Instruction I is writing to a register over here. If in an instruction J is dependent as a flow dependence on instruction I, you need to separate them enough in the pipeline so that instruction J gets the correct value. So what does that mean? Basically, instruction J needs to wait. You detect that there's a dependence and make instruction J wait. What does that mean? Instruction J stalls. It stays in the decode stage, one cycle. Not enough, because this instruction still hasn't finished writing to the register that instruction J needs. Stall one more cycle, not enough. And then stall one more cycle, now it's enough. So basically, we insert bubbles in the pipeline. Instead of this instruction moving in the pipeline, a no-op moves in the pipeline, no operation moves in the pipeline, and you don't do anything, clearly, that instruction doesn't need to do anything, you're basically stalling. And that's the idea, basically. The idea of a stall is to make the dependent instruction wait until its source data value is available. So what does it mean to stall? You stop all upstream stages. Upstream means younger instructions. Younger instructions stop, and all of the older instructions get out of the pipeline, right? Until the instruction that is actually causing the stall gets out of the pipeline, then you stop stalling. Okay. This is a good place to take a break, I think. And then we're going to talk about different ways of detecting as well as handling these data dependencies. And hopefully we'll get to fine-grained multi-threading as well. Nope. Okay, everything is good online? Okay, let's get started. So now we have defined pipeline stall. You know exactly what it means. You make the dependent instruction wait until its source data value is available, right? And to do so, you stop all upstream stages, meaning you stop all younger instructions, including fetch. So the program counter doesn't change. You basically are at the same instruction, same program counter at the fetch stage, same instruction you're decoding, same instruction you're executing wherever you are, basically. And you drain all the downstream stages so that the stall condition gets removed, right? You handle a long latency memory operation or long latency operation the same way. If an instruction needs to wait in the memory stage, you wait, meaning stall all upstream stages and drain downstream stages. And whenever the memory returns the results, you move on, okay? So it's a very general way of handling disruptions in the pipeline. Okay, so now let's talk about interlocking or detection of dependence. Essentially, interlocking is the detection of dependence between instructions in a pipeline processor to guarantee correct execution. And as we will see more and more in later lectures, there are ways of doing this in software, and there are ways of doing this in hardware. So there's software-based interlocking, meaning software detects the dependence between different instructions and does something about it. Reorders code, for example, such that dependencies are separated from each other such that they don't really cause a problem in the pipeline. Software ensures that the pipeline is always correct, moving, and full, if it's possible. It's a difficult task, but as we will see, there are ways of doing it. And if you cannot do anything, you can insert no-op instructions. No-op are no operation instructions that don't do anything, right? Clearly, that's not good for performance, right? Or you can do it hardware-based. Hardware-based meaning hardware detects the dependence between instructions. In modern processors, both are employed. We're going to talk about both, but we're going to especially look into hardware-based soon. Does anybody know the longer version of the MIPS acronym? MIPS is the ISA that we've been dealing with. And you never said what it was. Anybody? It's not millions of instructions per second. No one. I don't expect anyone to know this, but it's essentially, it actually stands for microprocessor without interlocking pipeline stages. So people who designed this instruction set architecture, their goal was to design a pipeline processor that's really simple. And they designed the ISA based on this assumption. And they wanted this microprocessor to not have any interlocking pipeline stages, meaning hardware interlocking. Their goal was to handle as much as possible in software. Now, that didn't work out very well. The latest MIPS processors are all very heavily doing hardware interlocking, meaning hardware dependence detection. And we will see the reasons, because that's better for performance. Okay, so there are two ways of detecting dependencies in hardware. One is scoreboarding. The other is combinational dependence logic check. Very quickly, I'll go through these, but you can think about these on your own. Essentially, scoreboarding means each register in the register file has a valid bit associated with it. We're going to see this later on in out-of-order execution also. An instruction, you're decoding an instruction, and whenever you're decoding an instruction, you figure out that this instruction is supposed to write to that register. It sets that valid bit at that point. It resets that valid bit at that point, saying that this register value you cannot trust, because I'm going to go through the pipeline, and at some point I'm going to write to this register, right? So for each register, you have some metadata saying whether you can trust the value in that register currently in the decode stage or not, right? An instruction, the decode stage checks if all its source and destination registers are valid. So in the decode stage, whenever you're decoding an instruction, the first thing you do is you check whether all your source and destination registers are valid, meaning you can trust the value. There's no one else in the later parts of the pipeline that are writing to this register. If that's the case, then you can continue, right? There's no dependence. But you reset your destination register. Okay, so this is how you detect dependence, basically. If all of your destination registers are valid in the decode stage, when you read the register, when you read these valid bits, you don't need to stall. There is no dependence. Otherwise, you stall the instruction. And of course, you need to make sure when an instruction actually writes to the register that it's supposed to write, you set the valid bit again, right, correctly, so that later instructions can continue. Okay, so this is a very simple way of detecting dependence and stopping instructions that depend on instructions that are later in the pipeline that's going to write to a register. The advantage is very simple, 1 bit for a register. Some people actually call these full empty bits. Is the register full or empty? Empty means somebody's going to write the value, and it's not written yet. The disadvantage is, unfortunately, this requires you to stall for all types of dependencies, not only flow dependencies. And you can think about why is that the case. There are ways of fixing that, but I'm not going to fix that. This is just an idea. I just want to give the idea of one way of doing it. Okay, so if you do that, what happens is, in the instruction decode stage, this load instruction, okay, let me go into the, okay, yeah. Okay, something happened over here, but this load instruction is, assume that it's writing to register 10. It's going to set the, it's going to reset the valid bit of register 10. When the subtract comes here, if it's reading from register 10, it'll see that the valid bit is 0, so it'll stop. Meaning it will not go. There is a stall condition, in other words. This register, this subtract will stay here. This other instruction that's being fetched over there will stay here. Load will move, and there will be a bubble inserted here, as we will see. And then load will move again. And once load actually finishes the write back stage, it resets the valid bit to 1. At that point, the subtract can move. Okay? So that's one way of doing it. A more aggressive way, which is a little bit more costly in hardware, is combinational dependence check logic. This is what's done in your book and in many books. There's a special logic that checks if any instruction in later stages is supposed to write to any source register of the instruction that is being decoded. This is a mouthful, but essentially it says whenever you're being decoded, you have some source registers, you check whether any of those source registers are going to be written to by any instruction that is in later stages in the pipeline. You can think of basically, you compare, there should be some comparators. For each source register, you have a comparator to the destination register of every instruction in later pipeline stages, right? Okay, assuming those instructions are writing, of course, you need to check that also, okay? So if the answer of that combinational dependence check logic is yes, for a given source register, there's at least one instruction in later pipeline stages that is writing to that register, or that's going to produce the value of that register, you stall the instruction in the pipeline. Otherwise, there's no need to stall because there's no flow dependence. So the advantage of this is there's no need to stall on anti and output dependencies. It's very clean. We just check for flow dependencies. The disadvantage is logic is more complex than a scoreboard. And logic becomes actually more and more complex as your pipeline becomes deeper and deeper. We have a very simple 5-stage pipeline here. If you make it 15 stages, then you need to check all of those stages downstream. And actually later, we're going to see something called superscalar execution. The idea is not have a single pipeline. The idea is to fetch multiple instructions in a given cycle. So replicate the pipeline. So now you need to check even more. Okay? But that's a later lecture, so patience on my part. Okay, so a pipeline operation, basically, what happens in this case? So subtract, for example, subtract. When it gets to this stage, there is some combinational hardware dependence check logic and we will actually briefly describe that logic later on, that checks whether register 10 is being written to by any instruction over here over here, over here. So how can you check that? Basically, you get the destination register IDs of instructions here, 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 and compare them to the source register 10. Okay, this is an equality checker. We built this in combinational logic, right? You have an equality checker. You have one equality checker that compares this to the destination register that's coming from here. So there needs to be some arc from here to here that gives the destination register ID. Here, here. So 3 equality checkers. Not only that, you should also check whether the instruction that is writing to that register is actually writing to that register, meaning there's a write signal to the destination register. You should also do the check for the other source. So there needs to be 3 more equality checkers. So there are a lot of equality checkers, as you can see, to check whether there is another instruction in the pipeline that's writing to the source that I'm reading at this point. And if yes, then you stall this because the value in the register file is not correct for you. You just need to wait for another instruction to finish. Okay, so that's detection. Once you detect, you can stall. But what else can you do? Basically, the observation is that dependence between 2 instructions is detected before the communicated data value becomes available. You can do this. You can say, okay, there's a load instruction ahead of me that's currently calculating its address, and I'm dependent on it because I know the destination register of both instructions. But I don't know the data value yet because load instruction did not access memory yet. It did not even generate address yet. It's in the execute stage. So one option is to stall the instruction right away, dependent instruction right away. The other option is to stall the dependent instruction only when it's really necessary, meaning you know whether the data value is available or not. Because the store, for example, the load instruction may actually have already accessed memory, but not have written to the register file yet. You can supply that data value early to the instruction that really needs it. This is called data forwarding and bypassing. And this is going to complicate the pipeline even more, but it's going to increase our performance also. There could be other options, as we will see later on too. Hopefully that makes sense. We're going to cover data forwarding, bypassing a lot today. Okay, so basically the problem we're going to solve is a consumer or dependent instruction has to wait in the decode stage until the producer instruction writes its value in the register file. That's the most conservative assumption we've had, right? So basically we don't want to do this. Our goal is to not stall the pipeline unnecessarily. We want to keep the pipeline moving, full and correct. The observation is that the data value needed by the consumer instruction can be supplied directly from a later stage in the pipeline instead of only from the register file, if it's available, if and when it's available. Okay? So a later instruction produces value, provide a bus or wire that supplies that data value to the instruction that needs it. And we know whether or not an instruction needs it because we built the data dependence checking logic earlier, data dependence detection logic. We know exactly what we're dependent on, right? So we can get that data value also when that data value becomes available. Does that make sense? Yes?
Would it make sense to add a few registers to cache directly in the pipeline?
Yeah.
Or not?
I mean, that's you're trying to optimize it maybe. It's possible, yes. Depends on the pipeline design. Potentially, you could actually have some internal registers to communicate these values. Yes, potentially. But let's not go there yet. Okay, so the idea here is to add additional dependence check logic and data forwarding paths and buses to supply the producer's value to the consumer right after the value is available. So we're not going to add a memory, but we're going to really directly supply with wires. If it's a 32-bit value, we're going to supply with 32 wires that value to the consumer. To the consumer, right after the value is available. And the benefit is that consumer now can move in the pipeline until the value can be supplied. So there's less stalling. You don't have to wait until the value is written to the register file. Okay. So this is a problem in a 5-stage pipeline. This becomes a much bigger problem if your pipeline is 20 stages. You don't want to wait in the decode stage when the value is actually available, but it's not written yet to the register file because you write to the register file at the end of the pipeline, right? So all of these ideas become much more powerful as your pipeline becomes deeper and deeper. And there's a reason why pipelines become deeper, to increase clock frequency, right? Okay, so now we're going to go into a little bit more detail to implement these data dependence handling concepts. So how do we implement stalling? So this is our pipeline that we constructed Actually, today we actually spent a lot of time constructing it. Stall. How do we stall? Essentially, to stall, we disable, let's say we want to stall the fetch stage over here. We disable latching the PC. We disable writing to this, writing into the PC. We disable writing into this register. And if we actually disable those, the instruction over here stays, right? The fetch stage doesn't move because you don't change the PC and you don't change the instruction over here. Oh, actually, the instruction over here also doesn't move because we don't write over here. So that way, you stall these two stages. You ensure that the stalled instruction in the decode stage stays here. Then the question is, of course, what goes here, right? You detected that instruction is dependent on some later instruction. You stalled here because you don't change this register. You stalled here because you don't change the PC. So these two stages are stalling right now. What goes into this register in the next cycle? Well, a bubble. Insert an invalid instruction or no operation into the stage following the stalled one. This is the one that's stalling because it's waiting for the data value to be available in the register file. Assume that we don't do forwarding right now. You need to insert a bubble. So how do you insert a bubble? Well, there are multiple ways of doing that, but you can basically invalidate or zero out the entire register so that control signals are all zeros. It's like a no operation, basically. Okay, so let's take a look at this data dependency example, and then we're going to build more of this stalling logic. So in this example, one instruction writes to register a register S0, and next instructions read this register. So all of them read S0, 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 as you can see, and this is the destination S0 in the first. So this is a read after write dependence. We're going to assume the trick that I mentioned earlier. Add can write into S0 in the first half of cycle 5. So we have this optimized register file where you can write into a destination register in the first half, and someone else can read in the second half. Okay. So you can see that these are the dependencies. And the instruction reads S0 on cycle 3, obtaining the wrong value. Clearly, we did something wrong. We didn't stall the end. Or reads S0 on cycle 4, again obtaining the wrong value. Only subtract will get the correct value. So basically, subsequent instructions read the correct value of S0 from the register file, including the subtract. So basically, wrong results happen only if the pipeline handles data dependencies incorrectly. That's why I don't like calling this a hazard, right? You need to make sure this doesn't happen. So, okay, this was one option, right? One option is to say, okay, I'm not going to add dependence checking logic. I'm going to punt to the compiler and tell the compiler, this is how my pipeline looks like. Schedule instructions such that this doesn't happen. Right? This meaning instructions getting incorrect results doesn't happen. This is one way of doing it, right? The same set of instructions, add over here, writing its result into destination register in the first half of the 5th clock cycle. Compiler was smart enough to insert 2 no-ops to make sure that the end instruction that's dependent actually gets the correct value. Basically, you needed to stall for 2 cycles. You need to, so one way is actually stalling and for 2 cycles in hardware. We're going to see that. The other way is actually a compiler detecting this and saying, okay, I'm going to actually insert 2 bubbles after this add. So essentially, insert enough independent instructions for the required result to be ready by the time it's needed by a dependent one. This requires a smarter compiler that understands the data dependencies clearly, but also the structure of the pipeline and how data can get communicated through the register file. So ideally, you don't insert no-ops, of course, right? Inserting a no-op means you're adding an instruction that is useless, right? Ideally, what does the compiler do? Reorders instructions such that independent instructions come after each other. And if you're able to do that, you can actually improve performance, right? And there are techniques to do that. We're going to talk about some of those when we cover very long instruction word architectures a few lectures later. But if the compiler cannot find any independent instructions to move or reorder, then it inserts no-ops in the end. But this is a powerful technique, as you can see, and this is purely software. The only thing that needs to happen is software, meaning the compiler needs to know the structure of the pipeline, which is a little bit more than what we have assumed so far from compilers. But if you have a smart compiler, it could know. You need to communicate, of course. Okay, so let's talk about data forwarding. So that was essentially detecting and eliminating the dependence so that you don't encounter it in hardware, right? Okay, So data forwarding is also called data bypassing. And the idea, again, is to forward the result value to the dependent instruction as soon as the value is available. And actually, we've already seen the basic idea before, not in the same context. Remember, we talked about data flow execution. In data flow, the principle is that data value is supplied to the dependent instruction as soon as it's available. And instruction executes when all its data operands are available. So essentially, data forwarding brings a pipeline closer to data flow execution principles. You really supply the data value when it's ready to a dependent instruction. We're going to see this more and more. We're going to actually bring the pipeline more and more into the data flow principles as we cover out-of-order execution also. So it's going to be very fascinating, I think. Okay, so data forwarding. Let's take a look at the locations in the data path. So these are, this was the same example that I showed you. Add is writing to S0, register S0. We're assuming that write happens into the register file in the first half of the 5th clock cycle, and is reading from that, and needs to read from that here. Like and is really beginning its execution really here, right? So actually and operation needs that value at the beginning of clock cycle 4. Now let's ask the question. Is the value S0, is the value that is named by S0, basically that is produced by this add instruction, available at the beginning of clock cycle 4? And the answer is yes. Yes, okay. Yes, then the answer is yes. So let's take a look at what happened to add. Add got fetched, decoded, executed, meaning it produced the value at the end of clock cycle 3 actually, and it latched the value to this register, to this pipeline register. Now, if you detected and is dependent on S0, you could take that value and put it as one of the inputs, the correct input, of course, of the ALU, and discard what you fetched from the register file, right? So and went through the pipeline while add was executing, it fetched from the register file S0, the wrong value, the old value of S0, which is not updated yet. But we also realize, because we designed the pipeline, that add actually produces its value here, and we can supply that directly to the input of the ALU at the beginning of the 4th clock cycle. So if we can provide that value directly over here and add a multiplexer, and that multiplexer chooses between the value coming from the value that we read from the register file or the value coming from this other register, as we will see later on, which is the pipeline register that's at the end of the ALU, then we can choose the value that's coming from the pipeline register at the end of ALU to get what was produced by add. Makes sense, right? So we add another path, another mux, another control. Yes? Yeah, you can do it, but that's a different concept, right? Yeah, this is just to supply the value that's produced to the consumer. But yeah, if a value is not needed later on, there could be ways of detecting it, but that's a very different concept. Yes?
Do we really connect it?
We're going to see it soon. Yes, you're going to see it soon. Yes. But this is just conceptual view of the thing. So essentially, we can supply this from the latched output of ALU to, latched output of the ALU to the input of the ALU. So we're going to see this implementation. But essentially, yes, you do connect. You need that thing. Also, let's take a look at another example over here, which is this OR. This OR needs that value when it's actually in the execute stage. And we know that add already produced this value. It's actually add is right now in the register file stage. It has not written to the register file yet, but it can supply the value directly from this pipeline register right back to the input of the ALU, so that this OR can actually execute with the correct value, right? So this is another forwarding path. There is one forwarding path from the output register of the ALU stage to the input of the ALU, another forwarding path from the output register of the memory stage to the input of the ALU, and then there's an internal forwarding path that we kind of assumed by a smart register file design. Whenever you write over here to the register file in the first half of the cycle. Another instruction that needs the value can get it in the second half of the cycle, right? But you could have added a muxes also, multiplexers to accomplish that as well. So these are the three forwarding paths in our pipeline, simple pipeline. Now let's take a look at how we implement it. Essentially, this is the implementation. What I just said, realized using wires and multiplexers. So this is ALU. Remember that add, it produces result. It's routed into this register, which is the pipeline register at the end of ALU. We take it, we add a wire that goes into either of the inputs of the ALU, because a dependent instruction may need it as the top input or the bottom input, right? And then we need some logic to select between them, of course, right? So basically from the latched output of the ALU to the input of the ALU. That's this example. Meaning you're forwarding the value produced by the instruction that's here to the instruction that's just starting executing, okay? Two instructions back to back. And then there's another forwarding path from here to here also. We're widening that mux now, multiplexer, because the value can also come from an instruction that has moved over here and also has done the computation, but has not written back to the register file yet. But we want to capture that value with another path. So we send that value, widen this multiplexer, change the control logic such that we actually decide which value to take. And then we also get that from the register file, which we assume there's some internal forwarding, which makes this picture easier, let's say. Assumption of that internal forwarding makes this picture easier, or a smarter register file. Half of the clock cycle you write, half of the clock cycle you read. Okay, so now you can see that this is not that bad, but it increased our complexity. And you can also specify the logic of how to control this mux. Essentially, if the instruction here is reading a register that's written by an instruction that's over here, you should get the data value from here. Otherwise, if it's reading a value that's written by an instruction that produces the value over here, you should get the data value over here. Otherwise, you should get it from the register file. Right? Why? Because you should get the latest definition of that value, latest version of the register that's written. This is the oldest instruction. This is the youngest instruction that writes to that register that you may need. So this is older, younger, youngest, if you will, right? Okay, so this is essentially the design of the forwarding. We basically now forward to execute stage from either memory stage or write back stage. And then I think I kind of answered this question earlier. When should we forward from either memory or write back stage? If that stage will write to a destination register and the destination register matches the source register that we're sourcing from. If both the memory and write back stages contain matching destination registers, which is possible, it's valid, it's allowed. Memory stage has priority to forward its data because it contains the more recently executed instruction. Basically, it says that you give priority to this red arrow clearly because it is the younger instruction that's producing the value. Okay? Okay, so if you want to specify this using some logic, your book does it. I will not go through it, but essentially, you can specify it, you can write it in Verilog. There's no magic after this. As long as you can describe the logic you're doing in a logical way, you can put it down as in Verilog, right? But you can read this in your book. It's basically in pseudocode, you can write it very, very easily. Okay, but you need to do it for both source registers, source register A, source register B, right? There are two source registers potentially for a given instruction. Okay, so that said, forwarding is not always possible. Depending on the structure of the pipeline and the latencies of instructions, you may not be able to forward data. In our pipeline, there's one case where we cannot forward data when you have a dependent instruction that follows a load instruction immediately. Forwarding is usually sufficient to resolve these dependencies, but there are cases when it's not possible due to pipeline design instruction latencies. For example, the load instruction is producing S0. When does the value become available? It becomes available after the load instruction actually accesses memory and gets the data value, right? When does the AND instruction actually get to the execute stage? In the same cycle. So basically, at the end of cycle 4, S0 becomes available, but AND instruction moves to the execute stage at the beginning of cycle 4. So it really needs the data value at the beginning of cycle 4, right? Essentially, its result cannot be forwarded to the execute stage of the next instruction, right? Well, it can be, but we break the critical path principle, meaning what we can do is exactly what this trouble arc says. We take the value from here, forward it here, and now we have a very long critical path, right? As opposed to having one memory access, latching the results, we have one memory access, get the data, supply it to the ALU, do the ALU operation, and then latch the data, right? So you don't want to do this forwarding because it doubles your critical path probably, something like that essentially. It breaks our critical path design principle essentially. So what happens is you need to stall the end in this case. This is the only condition where you need a stall unless you have like a long latency operation, which we're ignoring for now. Okay, so essentially stalling is necessary for this memory to execute dependence. So these instructions need to stall when that dependence is detected. So let's take a look at that stalling and dependence hardware, detection hardware. This is again from your book. You can see it more in your book. There's some dependence detection logic. So how do you actually stall? That's what I would like to point out over here. Your book has the complete picture, but essentially stall means the instruction in the decode stage should not move to the execute stage. Why? Because this end instruction is in the decode stage over here. It should stay in the decode stage, as you can see over here, right? It stays in the decode stage for 2 cycles until the value of the load word is available, and it can be forwarded here. This is a nice forwarding path, clean forwarding path. You get it directly from the latched output into the beginning or input of the ALU. We already added that forwarding path. This also needs to stall, of course, right? Okay. So in order to stall, you need to make sure later stages get inserted no ops. So your book does it by clearing the pipeline register in the stage where the instruction is stalling. This instruction is stalling over here. It cannot move. There should be something that moves into the pipeline register, and it's a no op essentially. So you clear the pipeline register such that no harm is done. It's a bubble. And then you actually have these enable bits, which I already discussed actually, that disable latching for this register such that this instruction doesn't move, and for this register, which is the PC, so that this instruction doesn't move. Okay? So we've already seen this, that put it in words, stalls are supported by adding enable inputs to the fetch and decode pipeline registers and clear inputs to the execute pipeline register in this simple pipeline. Or you can have an invalid bit associated with each pipeline register indicating that contents are invalid or valid and taking action based on that validity. There are multiple ways of implementing this that I will not go into detail over here, but the concept is simple. You need to insert a bubble basically. If you're stalling, you cannot move, but something else needs to move to the next pipeline stage, and that's a no-op. Okay? This is very similar to a compiler inserting a bubble, which is a no-op instruction, but the hardware is inserting it right now. Okay, so when a load word stall occurs, you keep the values in the decode and fetch stage pipeline registers, stall D and stall F are asserted, and you clear the contents of the execute stage register introducing a bubble. Okay, flush is also asserted, but I'm not going to go into that. So your book actually does a good job covering this if you are interested in learning more. But I've covered essentially everything you need to know. Okay, let's talk about control dependence right now, because this is going to actually occupy a lot of our time for some lectures after out-of-order execution. Data dependencies we've handled, hopefully, right? Memory, I think you know how to handle right now. If memory takes multiple cycles, you do the same thing. Stall everything that comes before, inject bubbles to everything that comes after, right? Anytime the pipeline cannot move, you know how to handle this right now. There's a general technique. What about control dependence? There's an elephant in the room over here, because control dependence is actually arguably bigger than everything that we have seen. So what is the control dependence? Control dependence is really some dependence on the program counter. It's really data dependence on the instruction pointer or the program counter. Meaning, okay, this is the question in control dependence. What should I fetch in the next cycle? I fetch this instruction, it moves to the decode stage. What should I fetch in the next cycle? Right. Well, you would say the address of the next instruction, right? And all instructions are dependent on previous ones. In a von Neumann machine, you have sequential execution. You increment the program counter by 4, right, in MIPS. So that's the reason why all instructions are control dependent on previous ones. So basically, by fetching the next instruction, PC plus 4, we're implicitly making an assumption. The next instruction is the next sequential instruction. Most of the cases this is true, meaning if the fetched instruction is a non-control flow instruction, next fetch PC is the address of the next sequential instruction. This is easy to determine if we know the size of the fetched instruction. We already do PC equals PC plus 4, and then we fetch the next instruction that way. But what if the instruction that is fetched is a control flow instruction? How do we determine the next fetch PC? Okay, that's a good question first. In fact, how do we even know whether or not the fetched instruction is a control flow instruction? We haven't decoded it yet. So we have a pipeline. We have the fetch stage. We have the decode stage. We fetch the control flow instruction. We don't know if it's a control flow instruction. Most of the decode stage. Only at the end of the decode stage, we know it's a control flow instruction. But we're already fetching the next instruction. Right? If this is a taken branch, then we fetch the wrong instruction. Right? So that's the problem. That's why this is so fundamental. Because of the sequential control dependence that we have and control flow dependence, we need to be very careful. So essentially, you can do something called branch prediction, which we will see more. This is a special case of data dependence, dependent on the PC. Remember, BEQ, conditional branch, is not resolved until the 4th stage of the pipeline, when we actually execute in the ALU, produce the result, latch the result, and then actually change the program counter from the latched output of the ALU. Instructions after the branch are fetched before the branch is resolved. So we kind of implicitly speculated. Essentially, fetch instructions into the pipeline without knowing that we should really have fetched them, right? So this is a simple branch prediction example. You always predict that the next sequential instruction is fetched. It's also called always not taken prediction. If you are wrong, you flush the not taken path instructions if the branch is taken. Basically, if the branch, you figure out whether or not the branch is taken when the branch executes, and you actually determine the condition. If the branch is actually taken, you flush all of the instructions. Flush means clearing all of those registers. So we know how to actually clear registers now, right? Okay? So basically, there's a misprediction penalty, number of instructions flushed when branch is incorrectly predicted. Penalty can be reduced by resolving the branch earlier. This is also called early branch resolution. Now let's take a look at that a little bit. This is our pipeline so far. A branch instruction, look over here. It's actually conditional branch, is resolved over here. Essentially, it's really updating the PC over here. So branch is here. Assume that the branch is not taken. We fetch the next instruction here, next instruction, next instruction here. Everything is good. Branch is not taken, so we did the right thing. If the branch was taken, when we execute the branch, it's taken. We fetch the next instruction over here, PC plus 4, but we should have fetched from the target. So this is wrong. Clearly, this is wrong. Clearly, this is also wrong because we fetch PC plus 4, PC plus 8, PC plus 12, whereas we should have fetched target plus 4, target plus 8, assuming none of those are branches either. Right? Okay. So basically, that's the problem. This is branch instruction. It resolves in cycle 4, and we have fetched 24, 28, 2C, as you can see, consecutive instructions. And when the branch instruction resolves, we need to change the program counter to 64, because you can calculate the target address, 40 plus 20 plus 4, PC plus 4 is 64. And that happens in cycle 5. When the branch is resolved in cycle 4, that gets communicated to the PC. In cycle 5, you fetch from the correct PC. And in the meantime, you need to get rid of these instructions that you fetched into the pipeline. Those are wrong. So you flush, meaning you clear those registers, right? That's it. You just need to clear those registers and you're done. Because those instructions did not do any harm so far. They did not write to any register. They did not write to memory because of the structure of our pipeline. As a result, we can do this. That sounds beautiful, right? So now you've seen the example of a simple branch misprediction. Okay, now let's try to make this a little bit better. We want to resolve the branches a little bit earlier. We can actually do that at the expense of some things. So branches, you actually know the register value. So let's look at the branch equal, right? Branch equal, it tests 2 registers. Register 1, register 2. You compare 2 registers. If they're equal, you basically set the program counter to the target target PC that you calculate. So basically, you can have an equality checker over here that you add after these registers. And then basically, if it's a branch and if the equality checker says equal, Then you basically select the program counter target address from the sign extended left shifted immediate, add it to PC plus 4. So you do the target address calculation here, and you also do the branch condition calculation in the decode stage. We move everything to earlier so that we don't flush more instructions than needed. And then you, of course, if it's a branch, you need to clear this one, right? That sounds good, right? You could do it. Clearly, this will have some benefit. If you do that, you need to flush only one instruction, right? You don't need to fetch these instructions. Basically, you fetch the next instruction, and the branch resolves at the end of clock cycle 2. So at the beginning of clock cycle 3, you're at the target address. So you fetched only one useless instruction, you flush only one of those. The question is it a good idea? Yes?
I mean, wouldn't we increase latency?
Exactly, yeah. So advantage, let's start with the advantage. You reduce the branch misprediction penalty. You reduce the cycles per instruction, which is good. Potentially, you increase the clock cycle time. In fact, probably you have increased the clock cycle time, meaning you have a higher clock period and lower frequency. You also have additional hardware cost in addition to increasing the clock cycle time. You have a specialized hardware that's likely not used by any other instruction. Right? Who else is going to use this hardware? Let's say no one, other than the branch. We do it to reduce the latency of the branches, but we increase the clock cycle time for every other instruction. Is that a good idea? Well, you need to evaluate, essentially. You need to evaluate based on this. You need to figure out how much did I reduce the average CPI? How much did I increase the clock cycle time? If the result is net positive, maybe this is a good idea, assuming the hardware cost is not too much, right? But based on what I know and based on this pipeline, it's probably not a good idea in this sort of pipeline. In some other pipeline, it may be a different thing. Okay, that's not the end of it. We forgot the data forwarding, meaning how can we resolve this branch? This works, what I just showed you works actually, only if the data values of registers are available for the branch to correctly calculate. What if they're not available? What if there are instructions over here that are writing those? And they're very likely instructions there because branch is actually dependent on some instructions that produce those registers. So you need to forward those registers. So whenever some computation earlier, you need to actually forward the data also. So there needs to be a forwarding path from here to here as well. Okay. So it adds even more complexity. It increases your critical path even more potential. This is from your book, Forwarding Logic. Essentially, this is the full store and forwarding logic. You stall because of an instruction is dependent on a load that has not produced its value yet, or you can stall because there is a branch, right? And that branch, you mispredicted the branch. And this is your final pipeline MIPS processor from your book. It includes always not taken branch prediction, early branch resolution, forwarding, and stall logic. It's complete, it's nice. What it doesn't include is multi-cycle memory or multi-cycle operations. That requires a little bit more work. So it's still not a realistic full pipeline. It's assuming magic memory with one cycle access. So, okay, doing better, smarter branch prediction. This was not so smart, right? We basically said, we're going to implicitly assume that PC will be incremented by 4, right? It's called always not taken for prediction. But you can be a bit smarter. You can guess whether or not the branch will be taken, right? And existing processors actually are quite smart. For example, backward branches are usually taken because loops iterate many times. If you see a backward branch, you basically predict it taken, right? You can keep a history somewhere in the processor, as we will see in later lectures, of whether a branch was previously taken, and you can improve the guess based on that history. If you've seen branch was taken 1,000,000 times, you say, okay, probably it's going to be taken again. You can be even smarter, as we will see. So accurate branch prediction requires the fraction of branches, or reduces the fraction of branches that causes a flush. There are many sophisticated techniques that are employed in modern processors to do accurate branch prediction. And the reason hopefully is clear. Because if you are incorrect in your prediction, you fill the pipeline with junk. Junk meaning useless instructions. You're going to flush them. So you'd better fill the pipeline with useful instructions. And the only way to do that is to predict the correct instructions to fetch from. So in fact, existing machines use simple machine learning methods to learn as well. Simple because hardware implementation of complex machine learning methods is too slow for high frequency operation. And we will see a lot of these in branch prediction lectures. So it'll be a fascinating overview of what people have done in 60 years of branch prediction, let's say. If you're impatient, you can watch the earlier versions. But hopefully not, we'll get to it. Okay, I think I do not have time to cover pipeline performance example. I will leave these slides for you to study. It's a very simple example, it's in your book also. And next week, we're gonna start with some other issues in pipelining, and then we're gonna build up to out-of-order execution. So have a good weekend. I'll see you next week.